Tonight, we're going to journey to a place so far from Earth that the sun, the same star that warms our skin every morning, would appear as nothing more than a slightly brighter point of light among countless others. A place where the very concept of solar system begins to lose its meaning. A place where gravity itself becomes so faint, so whisper-thin, that the smallest disturbance can change a body's fate forever. You've heard about the planets. You've heard about the asteroid belt and the Kuiper Belt, where Pluto drifts in icy silence. You've heard about Voyager 1 and Voyager 2 leaving the heliosphere and entering interstellar space. But beyond all of that, far beyond, lies something most people never think about. A vast, frozen shell of trillions of icy bodies surrounding our solar system in every direction. The Oort Cloud. And here's what most people don't realize. Anything that enters the Oort Cloud, whether a comet, a probe, or an object we haven't even imagined yet, faces a strange and almost cruel destiny. It can never truly be expected to come back. By the end of tonight, you're going to understand exactly why that is. Why the edge of our solar system functions less like a boundary and more like a point of no return. And what it means for everything we've ever sent into the dark. Before we begin, if you find these journeys into the deepest corners of space as fascinating as we do, take a moment to like the video or subscribe. It's a small action, but it makes a real difference in helping this channel reach more curious minds across the world. Now, let's begin. Think about how we usually imagine the solar system. A bright sun at the center, 8 planets in orderly orbits, a scattered field of asteroids, a distant ring of icy worlds beyond Neptune. That mental picture, the one you probably learned in school, is technically correct, but it is also wildly incomplete, because the planets and the Kuiper Belt only account for the tiniest portion of the sun's gravitational territory. Most of the solar system, by volume, is empty, or at least seemingly empty. The truth is that most of it lies in the Oort Cloud, a region so enormous it dwarfs everything else combined. Let's put numbers to it, because numbers help. Earth orbits the Sun at 1 astronomical unit, 1 AU, about 150 million kilometers. That's roughly 93 million miles. Neptune, the farthest planet, orbits at about 30 AU. The Kuiper Belt, where Pluto and countless other icy bodies drift, stretches from about 30 to 50 AU. That seems far. It feels far. But it's nothing compared to the Oort Cloud. The inner edge of the Oort Cloud is estimated to begin somewhere between 2,000 and 5,000 AU from the Sun. The outer edge stretches to somewhere around 100,000 AU, possibly even 200,000 AU. To translate that, the outer edge of the Oort Cloud may sit at roughly 1.5 to 3 light-years from the Sun. That's nearly halfway to the next nearest star, Proxima Centauri. Let that settle for a moment. The Oort Cloud is so vast that if you stood on one of its outermost objects and looked back, the next solar system over might be almost as close as your own. Our Sun would be just one bright star among many. You would not feel like you were in our solar system anymore. You would feel like you were standing at the edge of nothing. And yet, the Oort Cloud is filled with things. Trillions of icy bodies. Frozen remnants from the formation of the solar system 4.5 billion years ago. Pieces of the original cloud of gas and dust that collapsed to form the Sun and planets. Some of these objects are the size of mountains. Some are the size of small countries. They drift slowly, almost imperceptibly, on orbits that take millions of years to complete. Some take tens of millions of years. Some never complete an orbit at all because, before they can finish, something interrupts them. Here is where the mystery deepens. Out there, at the edge of the Sun's gravitational reach, gravity becomes incredibly weak. The Sun's pull at 50,000 AU is almost imperceptibly faint. A nudge that would barely register near Earth becomes a defining force at those distances. A passing star, light years away, can tug on Oort Cloud objects and change their trajectories permanently. The slow churn of our galaxy itself, the gravitational tide created by the Milky Way's distribution of mass, exerts a pull strong enough to lift objects out of their orbits. The Oort Cloud is not a stable, settled place. It is a frontier where every object is one disturbance away from being lost forever. This is why anything that enters the Oort Cloud or originates within it is rarely on a predictable path. Long-period comets that occasionally streak through our inner solar system come from the Oort Cloud. They appear, they swing around the sun, and most of them, after performing their brief, brilliant dance, are flung back out into the dark. Some return after millions of years. Some never return at all. They are ejected from the solar system entirely, sent drifting into interstellar space, alone, forever. And then there's the question of what humans have sent out there. Voyager 1, the most distant human-made object, has been traveling away from Earth for nearly 50 years. It crossed the heliopause, the boundary where the sun's solar wind gives way to interstellar plasma, in 2012. It is now considered to be in interstellar space. But here's the thing. Voyager 1 is not even close to the Oort Cloud. Not really. It is moving at about 17 kilometers per second, which sounds fast, and is fast, but at that speed, it will take roughly 300 years to even reach the inner edge of the Oort Cloud, and it will take an estimated 30,000 years to pass through the entire cloud and exit the other side. That number deserves to land. 30,000 years. Longer than the entire span of human civilization. Longer than the time since humans first developed agriculture. Voyager 1 will keep traveling, silent, dark, long after every person alive today is gone, long after the languages we speak are forgotten, long after the nations on Earth have risen and fallen many times over. And it will still be inside the Oort Cloud. Inside the place we are tonight going to explore. The place where things go and never quite return. Because that, in the end, is the central truth about the Oort Cloud. It is not just a region of space. It is a kind of one-way door. A boundary that once crossed changes the fate of whatever crosses it. Comets, probes, particles of dust, hypothetical missions of the future, all of them face the same strange reality. The Oort Cloud is a place you can enter, but rarely a place you can leave the way you came. And in the sections to come, we're going to uncover exactly why that is. To understand why the Oort Cloud behaves the way it does, we have to go back to the moment humans first realized it might exist. And that moment is more recent than you might expect. For most of human history, comets were considered omens. Ancient civilizations saw them as warnings from the gods, signs of impending doom, messengers of plague or war or the death of kings. Halley's Comet, perhaps the most famous of all, has been documented for over 2,000 years, with sightings recorded by Chinese astronomers as early as 240 BCE. The Babylonians tracked it. Medieval European chroniclers noted its passages. No one understood what it was. They just knew it appeared, blazed across the sky, and vanished. It wasn't until the late 17th century that Edmund Halley, an English astronomer, realized something extraordinary. The comet that bore his name was not appearing randomly. It was returning. He calculated, using the new laws of gravitation developed by his contemporary Isaac Newton, that the comet of 1682 was the same object as comets observed in 1607 and 1531. He predicted it would return again in 1758. He did not live to see his prediction proven, but the comet did return, right on schedule, and humanity gained its first concrete proof that these celestial visitors followed predictable, lawful paths around the sun. Comets, it turned out, were not omens. They were members of the solar system, just unusual ones, with long elliptical orbits that carried them far beyond the planets and then back again. But Halley's discovery raised an even stranger question. If comets like the one named after him orbited the sun on cycles of about 76 years, where did the other comets come from? Many comets observed over the centuries had orbits so long that calculating them with confidence was nearly impossible. Some came swinging in from distances no one could measure. Some had trajectories so steep that they seemed to plunge toward the sun from directions completely unrelated to the plane of the planets. They came from above, from below, from every angle imaginable. As if they had been falling toward us from a sphere surrounding the entire solar system rather than emerging from any particular direction. For centuries, this remained an unsolved puzzle. Astronomers catalogued comets. They tracked their trajectories. They wondered. But no one had a coherent theory for where the long-period comets, the ones with orbits stretching across thousands or millions of years, actually came from. There was simply not enough data. and not enough theoretical foundation to answer the question. Then came the 20th century, and with it, two crucial figures. The first was Ernst Öpik, an Estonian astronomer working in the 1930s. Öpik proposed that comets might originate from a vast reservoir of icy bodies located at enormous distances from the Sun, well beyond the orbits of the known planets. He calculated that such bodies could remain in stable, distant orbits for extraordinarily long periods, occasionally being perturbed by passing stars and scent falling inward toward the Sun. His paper, published in 1932, was a remarkable leap of imagination, but it received relatively little attention at the time. It was theoretical. There was no observational evidence. It was an idea waiting for someone to take it further. That someone was Jan Oort. A Dutch astronomer of formidable reputation, Oort had already made his name studying the structure of the Milky Way and demonstrating that our galaxy rotates. In 1950, he turned his attention to the problem of long-period comets. He gathered the most complete catalogue of cometary orbits available at the time and analyzed them statistically. What he found was extraordinary. The long-period comets seemed to have an upper limit on their orbital distances. Many appeared to be coming from a region roughly 50,000 AU from the Sun, and their incoming directions were essentially random, suggesting they originated not from a flat disk like the planets, but from a roughly spherical shell surrounding the entire solar system. Oort's paper, building on Öpik's earlier work, proposed that this shell was filled with billions, perhaps trillions, of icy objects. Most of them, he argued, were essentially undisturbed leftovers from the formation of the solar system itself, sitting in deep cold storage for billions of years. Occasionally, the gentle gravitational tug of a passing star or the broader influence of the Milky Way's gravity would dislodge one of these objects and send it tumbling inward toward the Sun, where after a journey of millions of years, it would appear in our skies as a long-period comet. The reservoir was named, fittingly, after the man who had given it form. The Oort Cloud was born, at least as an idea, but Oort's hypothesis raised an immediate follow-up question. How did the cloud get there in the first place? Why would trillions of icy bodies sit in a roughly spherical shell at such enormous distances from the Sun? The answer, developed over the decades following Oort's paper, lies in the violent early history of the solar system. About 4.5 billion years ago, the Sun and planets formed from a collapsing cloud of gas and dust. Most of the material that did not become the Sun ended up in a flat, rotating disk, which gradually coalesced into the planets we know today. But much of the leftover material, particularly icy bodies that formed in the outer regions near the orbits of what would become Jupiter, Saturn, Uranus, and Neptune, did not stay where it formed. The young gas giants were gravitational bullies. As they grew and shifted their orbits during the chaotic early period of the solar system, they flung enormous quantities of smaller icy bodies in every direction. Some were thrown into the Sun. Some were ejected from the solar system entirely, lost forever into interstellar space. And some, the ones whose trajectories happened to fall within a narrow range of possibilities, were thrown outward to enormous distances, where the gravitational pull of the Sun was weakened almost to nothing, but where the gentle influence of the wider galaxy could still hold them in loose, distant orbits. Those objects became the Oort Cloud, survivors of a violent gravitational lottery, sitting in cold storage ever since. This origin story has an important consequence for understanding why the Oort Cloud behaves the way it does today. The objects out there were placed by gravitational chaos. They were thrown outward in trajectories that just barely allowed them to remain bound to the Sun, sitting at distances where the Sun's grip is almost imperceptibly weak. They are, in a sense, on the gravitational edge, always have been. The very process that put them there left them vulnerable, balanced on the slimmest of gravitational margins. So when a passing star tugs or a galactic tide pulls, the response is dramatic. Objects shift, orbits change. Some fall inward and become comets. Some fall outward and leave the solar system entirely. In the next section, we'll explore what astronomers thought they understood about this distant region for most of the 20th century, the assumptions that seemed reasonable. The picture of the Oort Cloud as a quiet, frozen shell drifting in the dark, and then we'll begin to see how that picture started to crack. For decades after Jan Oort published his hypothesis, the picture of the Oort cloud that took hold in scientific minds was deceptively simple. Astronomers imagined a vast, quiet, spherical shell of icy bodies, drifting slowly in deep cold storage, virtually unchanged since the early days of the solar system. It was treated as a frozen archive, a library of primordial material, preserved by the cold and the dark and the sheer distance from the sun's warmth. Whatever chemistry, whatever ices, whatever organic compounds had existed in the protoplanetary disk 4.5 billion years ago, the Oort cloud was thought to have preserved them intact, undisturbed for the entire history of the solar system. The conventional wisdom was reassuring in its tidiness. The cloud was distant. The cloud was stable. The cloud occasionally released a comet into the inner solar system, and astronomers could study that comet to learn about the chemistry of the early sun's surroundings. It was elegant. It was orderly. And like most elegant, orderly pictures in astronomy, it turned out to be incomplete. The first assumption, the one most deeply ingrained in textbooks, was that the Oort cloud was essentially a single spherical shell. A roughly uniform distribution of objects extending from the inner edge, somewhere around 2000 AU, to the outer edge, somewhere around 100,000 AU. Astronomers spoke of it as if it were one structure, one population, one reservoir. The mental picture was of a thin, mostly empty sphere with comets sprinkled evenly throughout. Simple, memorable, easy to teach. The second assumption was that the cloud was dynamically calm. Yes, comets occasionally fell inward, perturbed by passing stars or by the galactic tide. But the perturbations were rare. The inner cloud was thought to be largely insulated from outside influences, and the overall structure was treated as having remained roughly constant over billions of years. Astronomers calculated that even close stellar encounters happened only every few 100,000 or few million years, and that the cumulative effect on the cloud, while significant over geological timescales, was slow and predictable. A few comets dislodged here, a few dislodged there. Nothing dramatic. The third assumption concerned origin. The Oort cloud was thought to be entirely the product of our solar system. The icy bodies out there were leftovers from the formation of the sun and planets, scattered outward by the young gas giants during the chaotic early period, and then settling into stable, distant orbits. Every object in the cloud, in this view, had been born here, had been part of our solar system from the beginning, had spent its entire existence circling our sun, however distantly. The fourth assumption was that the Oort cloud, while enormous, was a feature unique to systems like ours. It was assumed that other stars probably had similar reservoirs of distant icy bodies, but that those reservoirs were entirely separate, isolated from one another by the vast distances between stars. Each star kept its own cloud. Each cloud was a closed system. The Oort cloud was our Oort cloud, no one else's, and no other star's distant comets had any meaningful relationship with ours. These assumptions held for decades because they were reasonable. They fit the data available at the time. They explained the observed properties of long-period comets. They were consistent with the physics of solar system formation as it was understood through the mid-20th century. And critically, they were nearly impossible to test directly. The Oort cloud is so distant, its objects so small and so faint, that no telescope on Earth or in space has ever directly imaged a body in the Oort cloud at its rest position. Everything we know about the cloud comes from indirect inference, from the comets that fall inward, from statistical analysis of their orbits, from theoretical models of solar system formation. The cloud itself remains invisible. That invisibility made it easy to assume the cloud was simple. When you cannot see something directly, the simplest possible model often becomes the default because there is nothing to contradict it. Astronomers acknowledged uncertainty about the details, but the broad picture, a single spherical shell of locally formed icy bodies, drifting quietly through deep time, became the standard textbook description. It appeared in every popular astronomy book. It was repeated in every documentary about the solar system. Generations of students learned it, and for a long time it seemed sufficient. There were some uncomfortable details, of course. There always are. Some long-period comets had orbits that were difficult to explain with the simple model. Some seemed to come from distances closer than the assumed inner edge of the cloud. Some had compositions that differed slightly from what theory predicted. But these inconsistencies were treated as edge cases, anomalies to be resolved with refinements to the existing picture rather than fundamental rethinking. The basic story held. The Oort Cloud was a quiet, spherical, locally formed, dynamically isolated reservoir of primordial ice. End of story. It is worth pausing here to appreciate why this picture was so appealing. Science loves coherent narratives. A single elegant explanation that accounts for many observations is preferred over a fragmented patchwork of separate explanations. The simple Oort Cloud model fit that preference beautifully. It explained the existence of long-period comets, their random incoming directions, their apparent origin at great distances, and their connection to the early solar system, all with one structure and one mechanism. There was no obvious reason to complicate the picture without strong evidence that complication was needed. But here is something that anyone who has spent time studying science learns eventually. The universe rarely respects our preferences. Reality has no obligation to be elegant. And when we look closely at something we thought we understood, we often discover that the simple picture was a useful approximation, nothing more. The Oort Cloud was about to become a textbook example of this lesson. Over the last few decades, as telescopes improved, as computer models grew more sophisticated, as new observations accumulated, the simple picture began to develop cracks. Some of those cracks were small at first. Others widened quickly. And the more astronomers looked, the more they realized that the Oort Cloud was not what they had thought it was. It was not one shell, but possibly two, with very different properties. It was not entirely locally formed, with some evidence suggesting that other stars might have contributed objects to it during the Sun's early history. It was not dynamically isolated, with growing recognition that the galactic environment plays a far more active role in shaping its structure than previously believed. And it was not necessarily separate from the clouds of other stars, with researchers beginning to wonder whether stellar clusters might share objects, whether interstellar comets might be more common than anyone realized, whether the boundary between our Oort Cloud and the Oort clouds of other stars might be far more porous than the old picture suggested. These cracks did not appear all at once. They emerged slowly, over decades, as one observation after another challenged a piece of the standard picture. And the first major crack, the one that would set the stage for everything that followed, came when astronomers began to look more carefully at the inner regions of the Oort Cloud and found something they were not expecting. We will get to that in the next section. The first crack in the simple picture of the Oort Cloud appeared, fittingly, not from new telescopes pointed at the sky, but from new mathematics applied to old data. In the late 1970s and into the 1980s, astronomers began running more sophisticated computer simulations of how the solar system formed and evolved. They wanted to test whether the standard picture of the Oort Cloud, a single uniform spherical shell of icy bodies, could actually emerge from the chaotic conditions of the early solar system. They wanted to verify mathematically that the textbook story made sense. It did not, at least not entirely. The simulations consistently produced something different from what the standard picture described. They produced two distinct populations of objects, not one. There was an outer cloud, roughly spherical, extending from about 20,000 AU to 100,000 AU or beyond, populated by objects whose orbits were essentially randomized by billions of years of gravitational perturbations from passing stars and the galactic tide. That outer cloud matched the picture astronomers had long held. But the simulations also produced an inner cloud, a much denser, somewhat flatter region extending from roughly 2,000 AU to 20,000 AU, populated by objects whose orbits remained much more closely aligned with the plane of the planets. This inner region had a structure all its own. It was not a simple extension of the outer cloud. It was a distinct population, with different dynamics, different origins, and different behavior. This inner region eventually became known as the Hills Cloud, named after the astronomer Jack Hills, who proposed its existence in 1981. Hills argued that the inner Oort cloud, sheltered somewhat from the gravitational influences that randomized the outer cloud, would preserve more of the original conditions of the early solar system. It would be denser, it would be more massive, and it would behave differently when disturbed. Whereas a passing star might dislodge objects throughout the outer cloud relatively gently, a sufficiently close stellar encounter could trigger a comet shower from the inner cloud, sending a sudden burst of comets falling inward over a period of a few million years. The implications were striking. The simple picture had treated the cloud as quietly stable, releasing comets at a roughly steady rate. The new picture suggested that the rate could vary dramatically over time, with periods of relative quiet interrupted by intense bursts of cometary activity. This was the first major crack. The Oort cloud was not one structure. It was at least two. And the inner cloud, the Hills cloud, had the potential to send catastrophic waves of comets toward the inner solar system under the right circumstances. That possibility raised an immediately uncomfortable question. Could the great mass extinctions in Earth's history, the ones that wiped out the dinosaurs and other species, have been triggered by comet showers from the inner Oort cloud? The question remains open. The evidence is mixed. But the fact that the question could even be asked seriously was a sign that the simple picture of a quiet, harmless reservoir was no longer adequate. The second crack appeared from observation. As telescopes improved through the 1990s and into the 2000s, astronomers began to catalogue comets with greater precision than ever before. They tracked their orbits, measured their compositions, calculated where they had come from with increasing accuracy. And they began to notice something strange. The compositions of long-period comets were not uniform. They varied. Some comets seemed to contain ices and organic compounds consistent with formation in the outer regions of the early solar system, near the orbits of Uranus and Neptune. Others seemed chemically distinct, with isotope ratios or compound ratios that did not fit easily into the local formation story. This was, in itself, a small inconsistency. It could be explained by local variations in the protoplanetary disk, by differences in formation temperature, by the long history of cosmic ray exposure each comet had experienced. The variations were not so extreme as to demand a radical rethinking, but they raised a question that, until that point, had been considered settled. Were all the objects in the Oort cloud actually born here? Could some of them have come from somewhere else? In 2017, that question changed forever. A small object, just a few hundred meters across, was detected passing through the inner solar system on a trajectory unlike anything ever seen before. Its path was not bound to the sun at all. It was hyperbolic, meaning it had entered the solar system from interstellar space, was making a single pass around the sun, and would leave again, never to return. The object was named Oumuamua, a Hawaiian word meaning roughly scout or messenger from afar. It was the first confirmed interstellar visitor to our solar system, and its discovery was electrifying. 2 years later, in 2019, a second interstellar object was detected. This one, named Comet Borisov, was clearly a comet, complete with a tail of vaporized gases. Its trajectory, like Oumuamua's, was hyperbolic. It had come from somewhere else. It would leave again. And it was passing through our solar system as a temporary visitor. The discovery of these two objects in such quick succession had profound implications. If interstellar objects were passing through our solar system frequently enough that two could be detected within 2 years of each other, then the galaxy must be full of such objects. Trillions, perhaps quadrillions, of icy bodies drifting between the stars, ejected from their home systems long ago by gravitational encounters with their own gas giants. And if our solar system was being visited by such objects, then it stood to reason that some of them, over the 4.5 billion years of our solar system's existence, must have been captured. Not all interstellar objects passing through fly back out. Some, depending on their trajectory and the gravitational configuration at the time, get caught. They become bound to the sun, and the most likely place for them to end up, given the dynamics involved, is the outer Oort cloud. This was the third crack, and it was a major one. The Oort cloud might not be entirely ours. Some fraction of the objects out there, possibly a significant fraction, might have originated around other stars. They might have been ejected from those stars' systems billions of years ago, drifted through interstellar space for vast periods, and eventually been captured by our sun's gravity. They had become part of our Oort Cloud not because they were born here, but because they happened to wander close enough to be caught. How significant a fraction? No one knows with certainty. Estimates vary widely. Some researchers suggest that interstellar captures might account for only a small percentage of Oort Cloud objects. Others argue that during the sun's early days, when it was likely part of a dense stellar cluster, captures might have been far more common, and a substantial fraction of the cloud could be of foreign origin. The truth is somewhere in this range, and we may not know for certain for a long time. But the point is that the assumption of local origin, so foundational to the old picture, was no longer secure. The Oort Cloud, it turned out, might be a mixed population. Native bodies and immigrant bodies, drifting together in the dark, indistinguishable from one another at the distances involved, sharing the same fate at the edge of the sun's gravitational reach. And that fate, as we will see in the sections to come, is far stranger and more decisive than anyone first imagined. If the Oort Cloud is invisible, if no telescope has ever directly imaged an object resting at its proper distance, then how do we know anything about it at all? How can scientists make confident claims about a region of space we have never seen? The answer is a combination of tools, methods, and clever inference, built up over decades, that allows astronomers to study a place they cannot directly observe. Understanding these tools is essential, because without them, the Oort Cloud would remain a pure theoretical abstraction. With them, it becomes something we can probe, model, and slowly understand, even from a distance of trillions of kilometers. The first and most important tool is the long-period comet itself. Every long-period comet that falls toward the sun is, in a sense, a messenger from the Oort Cloud. By tracking its trajectory with great precision as it enters the inner solar system, astronomers can calculate where it came from. The orbit of a comet, like the orbit of any body under the influence of gravity, can be extrapolated backward in time. If you know its position and velocity at any point, and you know the gravitational influences acting on it, you can reconstruct where it has been. For long-period comets, this backward extrapolation typically leads to a region between 20,000 AU and 100,000 AU, exactly where the Oort Cloud is theorized to exist. Each comet, in effect, is a sample, a messenger carrying information about its place of origin, delivered free of charge to telescopes on Earth. The precision of modern astrometry, the science of measuring the positions of celestial objects, has made this approach remarkably powerful. With ground-based telescopes and orbital observatories like Hubble, astronomers can track a comet's position to within a tiny fraction of an arcsecond, which translates to an accuracy of a few hundred meters, even when the comet is hundreds of millions of kilometers away. By combining observations made over weeks or months, they can determine the comet's orbital parameters with enough precision to calculate where it spent the last several million years before falling inward. This precision is what has allowed astronomers to distinguish, statistically, between comets coming from the outer Oort Cloud, comets coming from the inner Hills Cloud, and interstellar visitors that are not bound to the sun at all. The second tool is spectroscopy. When sunlight reflects off a comet, or when the comet's ices begin to vaporize as it approaches the sun, the resulting light carries chemical fingerprints. Different molecules absorb and emit light at different wavelengths. By spreading the comet's light into a spectrum and analyzing which wavelengths are present and which are missing, scientists can determine what the comet is made of: water ice, methane, ammonia, carbon monoxide, organic compounds, isotope ratios that hint at temperature conditions during formation. Each comet becomes a chemistry sample from a region of space billions of kilometers away, with no need to actually travel there. This is how astronomers know that Oort Cloud comets contain ices and organic molecules consistent with formation in the early solar system. It is also how they have begun to notice subtle compositional differences between comets, the variations that first suggested some comets might not have originated in our solar system at all. The combination of trajectory analysis and spectroscopy gives astronomers two independent lines of evidence about each comet. One tells them where the comet came from, the other tells them what the comet is made of. Together, these two streams of information have allowed researchers to slowly build a picture of the Oort Cloud's composition, structure, and origin. The third tool is statistical analysis applied to large numbers of comets. Any individual comet is just one data point. But thousands of long-period comets have been observed and catalogued over the last few centuries, with the rate of new discoveries increasing rapidly as automated sky surveys have come online. By analyzing the entire population, astronomers can identify patterns that are invisible in any single object. The distribution of orbital orientations, the distribution of incoming distances, the frequency with which comets arrive from different directions. Each of these statistical patterns carries information about the structure of the cloud as a whole. If the cloud were a perfect uniform sphere, the patterns would look one way. If the cloud were flattened, they would look different. If the cloud had been recently disturbed by a passing star, the patterns would show a temporary excess from a particular direction. Modern sky surveys have transformed this analysis. The Pan-SDARS telescope in Hawaii, the Zwicky Transient Facility in California, and the upcoming Vera Rubin Observatory in Chile are systematically scanning the sky night after night, looking for faint moving objects. They are discovering comets at unprecedented rates, often catching them when they are still far from the sun, and behaving like the icy bodies they truly are before the heat of the inner solar system has changed their appearance. The data streaming in from these surveys is rapidly expanding the catalogue of long-period comets and allowing astronomers to refine their statistical models of the Oort Cloud with each passing year. The fourth tool is computer simulation. Sophisticated numerical models can now track the gravitational interactions of millions of test particles over billions of years, allowing astronomers to run virtual experiments. What happens to a population of icy bodies thrown outward by a young Neptune-like planet? Where do they end up? How does a passing star at 5,000 AU affect the structure of the resulting cloud over geological time? How do the gravitational tides of the Milky Way reshape the cloud's outer regions? These questions are nearly impossible to answer with pencil and paper because the systems involve too many interacting bodies and too many variables. But computer simulations can handle the complexity, producing detailed predictions about how the Oort cloud should look under various assumptions. The power of these simulations grew enormously through the 1990s and 2000s as computers became more powerful. Modern simulations can model the gravitational evolution of the early solar system with extraordinary fidelity, including the chaotic migration of the gas giants, the scattering of icy bodies in every direction, and the slow settling of survivors into stable distant orbits. The results of these simulations are then compared with the observed properties of long-period comets, and adjustments are made until the simulation matches reality. When a match is achieved, the simulation becomes a window into the unseen cloud, telling astronomers what its structure most likely looks like, even though they cannot directly observe it. The fifth tool, more recent and more speculative, is the search for direct detections of Oort cloud objects at their rest positions. This is extraordinarily difficult because objects in the Oort cloud are small, dark, and unimaginably far away. Even the largest Oort cloud bodies, possibly hundreds of kilometers across, will be far too faint to detect with current telescopes. But future observatories, particularly large infrared space telescopes, may eventually be able to detect the largest members of the inner Oort cloud, the ones closest to the sun and slightly warmer than the outer population. The Vera Rubin Observatory may also discover transitional objects, bodies whose orbits link the Kuiper Belt to the inner Oort cloud, helping astronomers map the boundary region between the two reservoirs. Together, these tools form a kind of indirect telescope, one that can see what direct vision cannot. Comets, spectroscopy, statistics, simulations, and the slow accumulation of observations over decades. None of them on their own is sufficient. All of them together have made the Oort cloud a place we can study scientifically rather than just imagine philosophically. And what these tools have begun to reveal, especially in recent years, is the first revelation in a series that has been quietly reshaping our understanding of the outer solar system. We will turn to that revelation next. The first major revelation about the Oort Cloud, the one that truly began to dismantle the simple picture, came from a careful analysis of long-period comet trajectories in the late 1990s and early 2000s. Astronomers had been accumulating data on these comets for decades, and as the sample grew, statistical patterns began to emerge that demanded explanation. The patterns were subtle, but they were real, and they pointed to something that no one had quite anticipated. The discovery was this: the long-period comets falling into the inner solar system were not distributed evenly in terms of where they came from. There was a clear excess of comets coming from regions of the cloud that should have been depleted long ago. According to the standard model, the inner edge of the Oort Cloud, the region between about 2000 AU and 20,000 AU, should have been thoroughly stripped of comets by billions of years of gravitational perturbations. Passing stars and the galactic tide should have either ejected those objects into interstellar space or dropped them into orbits where they would have been disrupted by the gas giants long before now. The inner cloud, in the simple model, should have been nearly empty, a region with so few comets that it should produce only the occasional rare visitor. Yet the data showed otherwise. Comets were arriving from this region in numbers that exceeded what the simple model predicted, not in vast quantities, but enough that the discrepancy could not be ignored. Something was wrong with the picture. Either the inner cloud was not as depleted as theory suggested, or there was a mechanism continuously replenishing it. Either way, the simple uniform sphere model could no longer account for what was being observed. This was the moment when the Hills cloud, proposed 2 decades earlier by Jack Hills as a theoretical construct, began to find serious observational support. The simulations had predicted that an inner Oort cloud should exist as a distinct, denser, somewhat flatter population. The observations now suggested that such a population did in fact exist and was actively contributing comets to the inner solar system. The two-zone model of the Oort cloud, an inner Hills cloud and an outer classical Oort cloud, moved from speculative hypothesis to working scientific framework over the course of perhaps 10 years. The scientific reaction was significant, but measured. Astronomers had long been comfortable with the idea that the Oort cloud was more complex than the textbook description, so the confirmation of a distinct inner population was not entirely shocking. What was striking, however, was the realization of just how dense the inner cloud might be. Estimates suggested that the Hills cloud could contain several times more objects than the outer cloud, perhaps trillions of icy bodies packed into a region that, while enormous by any everyday standard, was still much smaller in volume than the outer cloud. The implication was that the bulk of the Oort cloud's mass, perhaps the majority of all icy bodies bound to the Sun at great distances, lay closer in than previously believed. The reservoir was not just larger than expected. It was structured, it had layers, it had regions with very different properties, but the revelation cut deeper than a simple revision of structure. The discovery of the inner cloud's density forced astronomers to confront a darker possibility. If the Hills cloud is densely populated, then any sufficiently strong gravitational disturbance, a star passing close to the Sun, for instance, could dislodge not just a handful of objects but a flood, a shower. A sustained burst of comets falling toward the inner solar system over a period of a few 100,000 to a few million years. The simple model had treated cometary activity as roughly constant over geological time. The new picture suggested that activity could be punctuated by intense episodes, during which the inner solar system would be bombarded with comets at rates many times higher than the long-term average. This raised a question that had been lurking in the background of planetary science for decades. Could comet showers from the inner Oort cloud be linked to mass extinctions in Earth's history? The fossil record shows that life on Earth has been periodically devastated by extinction events, the most famous being the one that killed the dinosaurs 66 million years ago. That event is widely attributed to an impact in the Yucatan Peninsula and the question of where the impactor came from has been debated for decades. Was it an asteroid from the main belt between Mars and Jupiter? Or was it a comet, sent inward from the Oort Cloud by some gravitational disturbance long before? The truth is, we may never know for certain. The impactor was vaporized in the collision, and its origin can only be inferred from the chemical signatures it left in the geological record. But the discovery of a dense inner Oort cloud made the cometary hypothesis more plausible, not less. Some researchers went further, proposing that mass extinctions might occur on a roughly periodic schedule, perhaps every 26 to 30 million years, driven by regular gravitational disturbances of the inner Oort cloud. The idea, sometimes called the Nemesis hypothesis in its most speculative form, proposed that the Sun might have an undetected companion star whose orbit periodically brought it close enough to the Oort cloud to trigger comet showers. The Nemesis hypothesis has fallen out of favor due to lack of evidence for any such companion, but the more general idea that comet showers from the inner Oort cloud could play a role in shaping Earth's biological history remains a live area of research. Whether or not the comet shower hypothesis ultimately explains specific extinction events, the deeper implication of the inner Oort cloud discovery is harder to dismiss. The cloud is not just a quiet reservoir sitting in cold storage. It is a dynamic system that can respond to gravitational disturbances in dramatic ways. The objects out there are not safely tucked away on permanent orbits. They are balanced on gravitational margins so thin that even modest disturbances can change their fates. And once their fates are changed, once they are nudged inward or outward, there is no going back to where they came from. This is one of the first concrete reasons why anything that enters the Oort cloud cannot easily be expected to return. The cloud's dynamics are too sensitive, too responsive to perturbation. Once an object's orbit has been altered, the chance that it will ever return to its original position is essentially zero. The gravitational environment that put it on a new trajectory will continue to act on it, continuously, billions of years into the future. There is no restoring force. No mechanism to undo what has been done. The Oort cloud is, in a real sense, a record of changes. Every object out there carries the history of every gravitational interaction it has ever experienced, written into its current orbit, with no way to read backward to the original conditions. The discovery of the Hills cloud was the first revelation. It changed the structure of our understanding, but it was also a hint of something larger. The Oort cloud is more layered, more sensitive, and more active than anyone had assumed. And the deeper astronomers looked, the more they found that this was just the beginning. The next revelation would push the picture even further from the original textbook simplicity into territory that began to feel genuinely strange. The second major revelation came from looking at the Oort cloud in a completely different way. Instead of asking what was in it, astronomers began asking how it responds to the wider universe. And the answer turned out to be far more dramatic than anyone had expected. The Oort cloud, it became increasingly clear, is not isolated. It is not a self-contained system. It is deeply embedded in the gravitational fabric of the Milky Way, and the influences of that wider galactic environment shape it continuously, in ways that the standard picture had drastically underestimated. The first piece of this puzzle is what astronomers call the galactic tide. The Milky Way is not a uniform distribution of mass. It has a bright central bulge, a flat disk, a halo of dark matter, and a complex internal structure with varying density. As the Sun orbits the center of the galaxy, taking about 230 million years to complete one circuit, it experiences subtle but persistent gravitational tides from the surrounding mass distribution. These tides are imperceptible at planetary distances. The pull of the Milky Way on the Earth, for instance, is utterly negligible compared to the pull of the Sun. But at the distances where the Oort cloud sits, where the Sun's gravity has weakened almost to nothing, the galactic tide becomes one of the dominant forces shaping orbits. The mathematics of how this works is elegant in a quietly menacing way. The galactic tide exerts a directional pull that depends on where an object is relative to the plane of the Milky Way. Objects above or below the galactic plane are pulled toward it. Objects in particular orientations relative to the sun's motion through the galaxy experience torques that gradually alter the shapes of their orbits. Over millions of years, the tide slowly raises and lowers the perihelion distances of Oort Cloud objects, meaning the closest point of approach to the sun. An object whose perihelion is currently at, say, 10,000 AU might find itself slowly being shepherded by the tide so that, 10 million years from now, its perihelion has dropped to 200 AU, where it can be perturbed by the gas giants. Or it might be lifted, its perihelion raised to 30,000 AU, where it becomes essentially unreachable. The discovery that the galactic tide is the dominant mechanism for delivering long-period comets to the inner solar system, more important than passing stars in most epochs, was a major shift in thinking. For decades, stellar encounters had been considered the primary driver of cometary activity. The galactic tide had been treated as a secondary effect, a background influence less significant than the dramatic close passages of nearby stars. But by the late 1990s and early 2000s, detailed simulations had made clear that the tide does most of the work. Stars contribute occasional dramatic events. The tide does the steady, continuous reshaping. Both matter, but the tide is the engine that keeps the cloud connected to the inner solar system, day after day, century after century, across the vast spans of geological time. This was the second revelation, and it cut deeply into the simple picture. The Oort Cloud was not a self-contained system perturbed occasionally by external events. It was a structure permanently shaped by its galactic environment, with orbits in constant slow motion, never truly settled, never truly stable. The objects out there were not sitting in cold storage. They were drifting on tides invisible to us, riding currents that span the galaxy, slowly being repositioned by forces no one had appreciated fully until the computer simulations made it impossible to ignore. The implications were profound. For one thing, it meant that the Oort Cloud structure depends on where the sun is in its galactic orbit. As the sun moves through different regions of the Milky Way, the strength and direction of the galactic tide changes. During passages through denser regions, the tide is stronger, comet showers more frequent. During passages through emptier regions, the tide weakens, and the cloud becomes relatively quieter. Over billions of years, the sun has traversed many different galactic environments, and the Oort Cloud has been continuously sculpted by each of them. Its current structure is a product of this long history, a kind of geological record of the sun's path through the galaxy, written in the orbits of distant icy bodies. It also meant that the Oort Cloud, far from being a stable feature of our solar system, is a leaky structure. The galactic tide does not just deliver comets to the inner solar system, it also strips objects from the cloud entirely. Bodies whose orbits are lifted by the tide too far, beyond about 100,000 AU, drift into a regime where the sun's gravity can no longer hold them. They escape. They become interstellar wanderers, joining the populations of free-floating objects that drift between the stars. The cloud loses members continuously, not in dramatic events, but in a slow and steady leak, billions of objects ejected over billions of years. This raised a question that astronomers had not previously asked. If the Oort Cloud has been continuously losing objects to interstellar space for the entire history of the solar system, how many are still there now? The original models had treated the cloud as essentially full, populated with most of the icy bodies that had been delivered to it during the early solar system. The new picture suggested that the cloud might be significantly depleted, with the current population being only a fraction of what existed billions of years ago. Most of the original residents may have been lost to the galaxy long before the first dinosaurs walked the Earth. What we see today, in the form of long-period comets, is the residue, the survivors, the ones that have not yet been claimed by the galactic tide or by the next passing star. The second revelation also forced astronomers to think about passing stars in a more nuanced way. Stars do not pass close to the sun on any regular schedule, but over billions of years, many have come within a few light years of the sun, and a handful have come within 1 or 2 light years, deep into the Oort Cloud's territory. Each such passage disturbs the cloud. Each passage tugs at orbits, shifts perihelions, sends some objects inward and some outward, ejects some into interstellar space, and pulls others into tighter orbits. Astronomers have begun to identify specific stars that have made or will make close passes. Skols's star, a small binary system, is thought to have passed within about 52,000 AU of the Sun roughly 70,000 years ago, brushing through the outer edge of the Oort Cloud. Its effects on the cloud are still propagating outward, even now, in the form of subtle changes to orbits that will only manifest as cometary activity hundreds of thousands of years from now. This is one of the most disorienting features of the Oort Cloud. The effects of disturbances out there take a very long time to reach us. A comet whose orbit is altered today by a passing star will not arrive in the inner solar system for millions of years. The activity we see now is the result of events that happened in the deep past. The disturbances that are happening right now in the cloud at this very moment will produce comets that fall toward the Sun in geological epochs yet to come, by which time human civilization may no longer exist to witness them. The Oort Cloud, in this revelation, became a place where time itself behaves differently, a place where causes and effects are separated by millions of years, a place where every disturbance, however small, propagates forward into a future too distant for us to ever observe directly. And the next revelation, the one we will turn to next, would push the picture into territory stranger still. The third major revelation about the Oort Cloud emerged when astronomers began to recognize that a clear pattern was forming across all the observations and simulations of the past few decades. It was no longer just a matter of finding individual surprises. The surprises themselves were beginning to fit together into a coherent picture, and that picture was telling a story about the very nature of the cloud that no one had quite assembled before. The pattern was this. Every property of the Oort Cloud that astronomers had originally treated as stable, fixed, or characteristic of our solar system alone was turning out to be the opposite: variable, dynamic, shared with a wider galactic environment, and the implications of this pattern reached far beyond cometary science. To see the pattern clearly, consider what had been learned by the early 2010s. The cloud was not a single shell, but at least two distinct populations, an inner Hills cloud and an outer classical cloud, with very different dynamics and densities. The cloud was not isolated, but continuously sculpted by the galactic tide and by occasional passing stars, with its structure depending on the Sun's current galactic environment. The cloud was leaking objects into interstellar space at a slow but steady rate, having lost a significant fraction of its original population over billions of years. The cloud was probably mixed in origin, containing not just locally formed bodies, but possibly a meaningful fraction of objects captured from other stars during the Sun's early days in a dense stellar cluster. And the cloud's response to disturbances could be dramatic, with the potential to produce comet showers under the right circumstances. Each of these findings, taken alone, modified the simple textbook picture, but taken together, they pointed to something deeper. The Oort Cloud is not a feature of our solar system in the way that the planets or the Kuiper Belt are. It is a feature of our solar system's interface with the rest of the galaxy. It is the place where our gravitational territory ends and the gravitational territory of the wider universe begins. It is, in a quite literal sense, a boundary region. And like all boundary regions, it shares properties with both sides of the divide. It is partly ours and partly not. Partly stable and partly fluid, partly local and partly cosmopolitan. The pattern, once recognized, transformed how astronomers thought about the cloud's place in the broader picture of stellar systems. This pattern was reinforced by an observation that began to feel almost inevitable once it was made. The Oort Cloud is not unique. Every star with a similar formation history, every star that grew up alongside gas giants and emerged from a stellar cluster, should have a comparable cloud of distant icy bodies surrounding it. The simple textbook picture had acknowledged this in principle, treating other stars' Oort clouds as theoretical features that probably existed somewhere out there. But the new picture went further. Every Sun-like star has an Oort cloud, and if every Oort cloud leaks objects into interstellar space, then the galaxy must be filled with the ejected debris of countless stellar systems, not just a few interstellar visitors like Oumuamua and Borisov, an enormous, continuously refreshed population of icy bodies drifting between the stars, contributed by every Oort cloud of every star in the galaxy. Astronomers began to estimate the size of this interstellar population. The numbers were staggering. Calculations suggested that the Milky Way could contain quadrillions of free-floating icy bodies, possibly more, the cumulative product of billions of years of cometary leakage from countless stellar systems. Some of these objects would be tiny, just a few hundred meters across, like Oumuamua. Some would be larger, more substantial, capable of producing dramatic cometary displays if they ever fell into a stellar system. They would be invisible to current telescopes most of the time, dark and cold and far from any star, only becoming briefly detectable during the rare moments when one happened to pass close enough to be illuminated. The galaxy, in this view, is far less empty than it appears. The spaces between the stars are not vacant. They are filled with the slow drift of ejected solar system fragments, an enormous reservoir of material that has been homeless for billions of years. And this raised a possibility that began to reshape how astronomers thought about Oort clouds in general. If the galaxy is full of these wandering objects, then any star, including our own sun, must occasionally capture some of them. The capture process is statistical. Most objects passing through a stellar system on hyperbolic trajectories will leave again, like Oumuamua and Borisov. But a small fraction, depending on the precise geometry of their approach, will be slowed enough by gravitational interactions to become bound. They will join the host star's Oort cloud, becoming permanent residents of a system they were not born in. Over the lifetime of a star, the cumulative number of such captures could be significant. Some studies suggest that our Sun, during its 4.5 billion years of existence, may have captured millions or even billions of interstellar objects, depending on the assumptions one makes about the density of interstellar wanderers and the efficiency of the capture process. This is the third revelation, and it is in many ways the most philosophically unsettling. The Oort cloud, as it exists today, may not be just a record of our solar system's formation. It may be a record of our solar system's encounters with the rest of the galaxy. Every star our sun has passed near, every dense region of space it has traversed, every interstellar cloud it has moved through, may have left some trace in the form of captured objects now drifting in the Oort cloud alongside the native population. The cloud, in this view, is a kind of archaeological site, layered with deposits from different epochs of the sun's journey through the Milky Way. Some objects are originals, present since the early days of the solar system. Some are immigrants from the sun's birth cluster, captured during the chaotic period when the sun was still surrounded by hundreds or thousands of sibling stars. Some are more recent arrivals, captured during the sun's long subsequent journey through the galaxy. Distinguishing these populations is extraordinarily difficult. The objects involved are too small, too distant, too faint to be characterized individually. But statistical signatures may emerge over time, especially as new telescopes come online and as the catalogue of long-period comets and interstellar visitors grows. If certain comets show chemical signatures, isotope ratios, or compositional features inconsistent with formation in our early solar system, they may be flagged as candidates for foreign origin. Over decades or centuries of careful observation, the proportion of native to immigrant objects in our cloud may eventually be estimated, giving us a quantitative measure of how much of our Oort cloud is truly ours. The pattern, then, is one of profound interconnection. The Oort cloud is not a closed system. It is part of a larger galactic ecology, exchanging material with the wider universe over geological time. Objects flow in and objects flow out, carried by tides and stellar encounters, by capture and ejection. Every Oort cloud is connected, however tenuously, to every other Oort cloud. The galaxy is one enormous network of stellar systems, each surrounded by its own cloud, each leaking and receiving in turn, each contributing to and drawing from a common pool of icy debris that drifts between them. This is part of why anything that enters the Oort cloud cannot truly be expected to return. The cloud is not a place, it is a phase. a region of perpetual exchange where boundaries blur and origins become uncertain. And the next revelation will take us deeper still, into territory where the paradox of the Oort Cloud becomes impossible to ignore. The fourth revelation about the Oort Cloud is the one that most directly confronts the paradox at the heart of this entire story. It is the discovery that has emerged not from a single observation or a single simulation, but from the gradual realization that the mathematics of the cloud itself contains something deeply strange. Something that, once you see it, changes how you think about boundaries, about gravity, about what it means for an object to belong to a star system at all. The Oort Cloud, it turns out, exists in a regime where the very concept of being bound to the sun begins to break down. To understand what this means, we have to revisit something we touched on earlier and look at it more carefully. The sun's gravitational influence does not have a sharp edge. There is no specific distance at which the sun stops pulling on things. Gravity, as Isaac Newton recognized over 3 centuries ago, extends infinitely in principle, weakening with distance according to the inverse square law. An object 100 AU from the sun feels less gravity than one 10 AU away, but it still feels something. An object 10,000 AU away feels even less, but the pull is not zero. An object 100,000 AU away feels gravity so faint that it is almost imperceptible, but the sun is still tugging. There is no clean boundary. This means that defining where the solar system ends is genuinely difficult. Astronomers have used different definitions for different purposes. The heliopause, where the sun's solar wind meets interstellar plasma, lies at about 120 AU and is sometimes called the edge of the heliosphere. The gravitational sphere of influence, often called the Hill sphere of the sun, extends much further, to perhaps 100,000 to 200,000 AU, depending on assumptions about the local galactic environment. Some definitions place the edge at the orbit of Neptune, others at the Kuiper Belt cliff, others at the inner Oort Cloud, others at the outer Oort Cloud. There is no single answer because there is no single boundary in nature. Here is where the paradox sharpens. Objects in the Oort Cloud are, by definition, bound to the sun. Their orbits are closed, meaning they will eventually return to roughly their starting positions after enormous periods of time. But the bond is so weak, so easily disrupted, that the distinction between bound and unbound becomes almost meaningless. An object at 50,000 AU on a closed orbit might be one passing star away from becoming unbound. It might already be in the process of becoming unbound, with the disturbance still propagating through its orbit, not yet apparent to anyone watching. Whether it counts as a member of our solar system depends on a calculation that involves not just the sun's gravity, but the gravitational influences of every nearby star, every passing galactic structure, every tide and torque acting on it across millions of years. Membership in the Oort Cloud is provisional. This is the unexplainable, paradoxical element. The Oort Cloud is, in a real sense, both inside and outside our solar system at the same time. It is bound by definition, but practically free. It is ours by gravitational accounting, but constantly being claimed by the wider galaxy. Its objects are members of our system in the same sense that someone standing on the threshold of a doorway is in the room. Technically, yes. Practically uncertain. One step in either direction changes the answer. The mathematical structure underlying this paradox is what astronomers call orbital chaos. At small scales, orbits are predictable. The orbit of Earth around the Sun can be calculated thousands of years into the future with extraordinary precision. The orbit of Pluto can be projected forward by tens of millions of years with reasonable confidence. But at the distances of the Oort Cloud, where the Sun's gravity is so weak that small perturbations dominate the dynamics, orbits become chaotic in the technical mathematical sense. Tiny differences in initial conditions lead to enormous differences in long-term outcomes. The position and velocity of an Oort Cloud object today cannot reliably predict its position and velocity a billion years from now, because the cumulative effects of countless small disturbances make the long-term trajectory effectively unknowable. This is not a failure of measurement. It is not a problem that better telescopes will solve. It is a feature of the dynamics themselves. The system is sensitive to initial conditions in a way that makes long-term prediction impossible in principle. An object that we observe today in a particular orbit might, over the next billion years, follow any of a vast number of possible trajectories, depending on the precise sequence of perturbations it experiences. Some of those trajectories keep it in the cloud. Others send it falling toward the sun. Others eject it into interstellar space. We cannot tell which path any particular object will take, even with perfect information about its current state, because the chaos amplifies tiny uncertainties into enormous divergences. This chaotic dynamics has a deep consequence that is worth sitting with. For any object in the Oort Cloud, the question of whether it will return to its current position over the next orbital period is, in a meaningful sense, undecidable. Its orbit is so long, the perturbations it will experience are so numerous and so unpredictable that the very notion of a return to its starting point loses precise meaning. The orbit is not a fixed ellipse that the object traces over and over. The orbit is a slowly evolving path that changes with every perturbation, every galactic tide, every passing star. An object that appears to be on a million-year orbit today may, by the time it actually completes that orbit, find itself on a completely different orbit, having been reshaped by forces acting on it throughout its journey. This is why probes like Voyager, even though they are technically still gravitationally bound to the Sun in some calculations, and unbound in others, depending on how the calculation is done, will not return in any meaningful sense. The math is not the kind of math that produces predictable, periodic returns. The math is the kind of math that produces ever-divergent trajectories, paths that wander through a vast space of possibilities, paths whose long-term behavior cannot be predicted, and which, in practice, almost never bring an object back to where it started. The Voyager probes, by the way, deserve a moment of attention here. They are not on Oort Cloud orbits. They are on hyperbolic trajectories, meaning they have enough velocity to escape the Sun's gravity entirely. They will not enter Oort Cloud orbits as residents. They will simply pass through the cloud's territory, drifting outward at constant speed until they reach interstellar space and continue onward indefinitely. The Voyagers are not returning. They are not on closed orbits. They are leaving forever. And the same is true of any future probe sent on a similar trajectory. Once it acquires enough velocity to cross the threshold of escape, it joins the population of objects flowing outward from our solar system, contributing in its own tiny way to the galactic ecology of interstellar debris. Even objects that remain technically bound to the Sun, however, face the paradox. Their bondage is so weak, so contingent, so easily revised by external influences that they cannot be relied upon to return to anything resembling their original orbits. The Oort Cloud is the place where the dream of orderly, predictable, returning motion meets the reality of chaotic, perturbation-dominated dynamics, and the reality wins, every time. The cloud is a place of one-way journeys, regardless of whether the object in question is technically bound or unbound. The mathematics simply does not support reliable returns at those distances. And that mathematical truth, the one that emerges from the very structure of how gravity behaves at the limits of stellar influence, is what we will explore as the central revelation. Everything we have discussed so far has been building toward a single, fundamental truth. A truth that, once you see it clearly, reframes not just the Oort Cloud, but the very nature of our solar system's place in the universe. Tonight, we arrive at that truth. The most shocking revelation about the Oort Cloud is this. It is not really a part of our solar system in the way we have always imagined. It is the boundary itself, the transition zone, the place where the very concept of belonging to a star dissolves into something else entirely. And once an object enters that zone, the rules that governed it before no longer apply. Let me explain what this means by going back to first principles. Imagine for a moment that you could shrink the entire solar system down to a scale model. Place the Sun at the center of a soccer field. On this scale, Earth would be a small marble about 30 meters from the Sun. Neptune would be a slightly larger marble, nearly a kilometer away. The outer edge of the Kuiper Belt would be about 1.5 kilometers out. So far, the model is manageable. You could walk it. You could see it. The system has a recognizable structure with clear distances and clear relationships. But now place the inner Oort cloud on this scale. It would begin about 60 kilometers from the Sun. The outer Oort cloud would extend out to roughly 3,000 kilometers. On a soccer field scale, the Oort cloud is the size of a continent. The planets and the Kuiper Belt occupy a single field at the center of that continent. Everything else is Oort cloud territory. This is what most people never grasp about our solar system. The familiar parts, the planets, the asteroids, the Kuiper Belt, all of it, are clustered in a tiny central region. The vast majority of the Sun's gravitational territory is Oort cloud. By volume, by extent, by sheer expanse, the Oort cloud is the solar system. The planets are an afterthought, a small bright concentration at the center of an enormous, mostly empty sphere. And the boundary between this enormous sphere and the rest of the galaxy is not a sharp line. It is a gradient, a slow fade, a region where the Sun's authority weakens until it can no longer claim authority at all. This is the revelation. The Oort cloud is the gradient itself. It is not a structure floating in our solar system. It is the long, gradual interface where our solar system becomes the galaxy. Inside the Kuiper Belt, the Sun is clearly in charge. Beyond 100,000 AU, the galaxy is clearly in charge. In between, somewhere across that vast intermediate range, control is shared, contested, ambiguous. The Oort cloud is the contested zone, the place where neither the Sun nor the galaxy fully owns the objects within it. The place where membership in our solar system is not a fact but a probability calculated based on a delicate balance of forces that can shift at any moment. This understanding changes how we should think about anything entering the Oort cloud. A comet falling inward from the cloud is not arriving at the edge of our solar system. It is being released from a contested zone, momentarily captured by the Sun's stronger inner gravity, briefly making itself visible to us before being flung back into ambiguity. A probe launched from Earth on a trajectory that takes it outward into Oort cloud territory is not extending our reach into our own backyard. It is being released from the Sun's clear authority into a region where authority is shared, where the probe's future is determined as much by the galaxy as by the Sun, where the very category of belonging becomes uncertain. This is why nothing that enters the Oort cloud can be expected to return in any meaningful sense. The cloud is not a destination from which you depart and to which you return. It is a phase transition, a boundary you cross. Once an object is in the cloud, it has joined a population whose behavior is governed by mixed forces, by chaotic dynamics, by perturbations from the entire surrounding galaxy. It is no longer purely a member of our solar system. It is a candidate for membership in many systems, including our own, with the outcome of that candidacy depending on factors that cannot be predicted and that may take millions of years to resolve. The implications cascade outward from this central insight. If the Oort cloud is the boundary itself, then every Oort cloud around every star in the galaxy is also a boundary. The galaxy is not a collection of star systems separated by empty space. The galaxy is a collection of star systems with overlapping boundary regions, each system's Oort cloud potentially touching or even interpenetrating its neighbor's clouds when stars pass close enough. The boundaries are not walls. They are zones of mixing, of exchange, of shared territory where objects can transfer from one system to another over geological time. The galaxy, in this view, is a single interconnected ecology of stellar systems, with the Oort clouds serving as the membranes through which material flows between them. This is a profoundly different picture from the textbook image of isolated stellar systems separated by vast empty distances. The distances are vast, yes. The stars are far apart, yes. But the boundaries of stellar systems extend so far outward that, even at these enormous distances, they meet, they touch, they share. The galaxy is not a sparse archipelago of isolated islands. It is a dense network of overlapping gravitational domains, with the Oort clouds serving as the contact surfaces between them. This reframing has a strange emotional weight to it. We have always thought of our solar system as our home, a discrete place, a bounded region with the Sun at the center and a clear, if distant, edge. The new picture suggests that our home is more open, more porous, more connected to the wider universe than we have ever appreciated. The Oort Cloud is not a wall that defines where we end. It is a doorway, a long, gradual doorway, opening in every direction, through which material has been flowing in and out for billions of years. We are not alone in a bubble. We are connected to every other star in the galaxy by these long doorways. The connections are slow. The exchanges take millions of years, but they are real, and they are continuous, and they have been shaping our solar system for as long as the solar system has existed. And there is something almost vertiginous about realizing this. The frozen comets out there, drifting in the Oort Cloud's contested zone, may not all be ours. They may include refugees from other stars. They may include objects that have been claimed and released by the Sun multiple times over the eons. They may include bodies that are themselves on their way out, having been given a gentle push by the most recent passing star. Now slowly drifting toward the gravitational territory of some other star they may not reach for another 100 million years. The cloud is a kind of slow conversation between our Sun and the galaxy, conducted in the language of orbital mechanics, exchanging messages over timescales that dwarf the entire history of life on Earth. This is the climactic insight. The Oort Cloud is the boundary, the gradient, the contested zone, the doorway. Anything that enters it has crossed into a region where the rules of our solar system no longer apply cleanly. And the implications of this, the implications that ripple outward into our understanding of cosmic dynamics, planetary history, and the future of human exploration, are what we will turn to next. The revelations we have explored so far do not just modify our picture of the Oort Cloud. They reshape several of the most fundamental ideas in planetary science, ideas that have guided how astronomers think about stellar systems for more than half a century. To understand the scope of this change, it helps to walk through the old theories that have been quietly overturned and see what has replaced them. The shift is not just a matter of new details added to old frameworks. It is a fundamental rethinking of what stellar systems are and how they relate to the wider galaxy. The first overturned theory is the closed system view of stellar formation. For most of the 20th century, planetary scientists treated each star and its surrounding planetary system as essentially independent. The story went like this. A cloud of gas and dust collapsed under its own gravity. A star formed at the center. The remaining material formed a disk that gradually coalesced into planets and smaller bodies. Once the system stabilized, it stayed stable, evolving slowly under the influence of its own internal dynamics. Other stars existed nearby, but their influences were treated as negligible perturbations. The system was, for all practical purposes, a closed unit, isolated by the vast distances between stars. This view is no longer tenable. The Sun's early environment, the dense stellar cluster in which it likely formed alongside hundreds or thousands of sibling stars, was a place of constant gravitational interaction. The Oort Cloud's outer reaches probably acquired members from other stars during this period, while losing members to other clusters in turn. The closed system was never closed. Stellar systems are now understood to form in open environments where material is exchanged between neighbors, where the boundaries are porous from the beginning, and where the final structure of a system reflects not just its own internal dynamics, but the influence of every star that was nearby during its formative epoch. Our solar system is not the product of an isolated event. It is the product of a stellar neighborhood, shaped by encounters and exchanges that have largely been forgotten, but that left lasting traces. The second overturned theory concerns the source and frequency of cometary visitors to the inner solar system. The old picture treated comets as primarily originating from a stable, mostly undisturbed reservoir, with a roughly constant delivery rate maintained by the steady action of stellar encounters and galactic tides. Comets came. Comets went. The rate was relatively predictable on geological timescales. This view supported a relatively passive picture of Earth's relationship with the outer solar system, in which the inner planets occasionally received cometary visits but were not subject to dramatic variations in cometary activity over time. The new picture undermines this stability. The discovery of the dense Hills cloud, combined with the recognition that close stellar encounters can trigger comet showers, means that cometary activity has likely varied dramatically across Earth's history. There have been periods of relative quiet, when the Oort cloud was undisturbed and few comets reached the inner solar system. There have been periods of intense activity, when a recent stellar encounter or galactic transit triggered a flood of comets falling inward over a few million years. Earth's history, including possibly its biological history, may have been shaped by these variations in ways we are only beginning to appreciate. The idea that life on Earth has been protected by a quiet, predictable outer solar system is no longer secure. The outer solar system is a more active participant in our planetary history than previously believed. The third overturned theory involves the identification of native versus foreign material in our solar system. The old picture assumed that everything in the solar system, including the Oort cloud, was native, born here, formed from the same protoplanetary disk that produced the Sun and the planets. Every comet, every asteroid, every distant icy body was a piece of our own origins, an archive of the chemical and physical conditions of the early solar system. Studying comets meant studying our own past. This assumption is no longer reliable. The Oort cloud likely contains some fraction of objects captured from other stars, either during the Sun's cluster phase or during subsequent stellar passages. The chemistry of these objects may differ from the chemistry of native bodies, but distinguishing them is enormously difficult given the small number of comets that have been studied in detail. When astronomers analyze a long-period comet, they cannot easily tell whether they are looking at a piece of our own protoplanetary disk or a piece of someone else's. This uncertainty cuts into the fundamental project of using comets to reconstruct the early solar system. Some of the comets we have studied may not be telling us about our solar system at all. They may be telling us about a different one that ejected the object in question billions of years ago and whose star may no longer even be identifiable. The fourth overturned theory is the simple model of how planetary systems lose material over time. The old picture had a relatively neat description. Material formed in the protoplanetary disk. Some of it became planets. Some of it became smaller bodies. Some of it was ejected during the chaotic early period of gas giant migration. Once the system stabilized, the inventory was essentially fixed, with material being lost only through rare events like cometary impacts on planets or escapes from the system. The mass of a stellar system was treated as roughly conserved over time, with only minor losses across billions of years. The new picture is much more dynamic. The Oort cloud is continuously leaking material into interstellar space, with billions of objects ejected over the lifetime of the solar system. This loss is not catastrophic in any individual epoch, but it is significant over geological time. The solar system has been steadily shrinking, in a sense, as its outer reaches lose members to the galaxy. At the same time, occasional captures bring new members in. The balance of these flows determines the long-term evolution of the Oort cloud's population. Stellar systems, in this view, are not static reservoirs of fixed material. They are flowing systems, with material entering and leaving continuously, contributing to and drawing from a galaxy-wide pool of icy debris. The fifth, and perhaps most quietly profound overturned theory concerns the very definition of a stellar system. The old picture treated stellar systems as well-defined objects with clear boundaries. You could ask how many stars there were in the galaxy, how many planetary systems existed, how many comets each system contained, and these questions had crisp answers in principle, even if the data was incomplete. The new picture makes some of these questions surprisingly slippery. Where does our solar system end? At the heliopause, at the inner Oort cloud, at the outer Oort cloud, at the gravitational sphere of influence? The answer depends on what you mean by the question, and different definitions produce different answers. The system has no sharp edge. Its boundary is a gradient, and that gradient is part of the system itself. This means that questions about the inventory of our solar system, the total number of objects belonging to the Sun, the total mass of the Oort cloud, become questions of definition as much as observation. The numbers we cite for these quantities depend on where we choose to draw the line, and the lines are arbitrary, conventions adopted for convenience, not natural features of the universe. The Oort Cloud has taught us that the universe does not respect the boundaries we draw around things. It produces gradients, transitions, mixing zones, and we have to adjust our conceptual frameworks to match this reality. Each of these overturned theories represents a significant shift in how scientists think about planetary systems. Together, they amount to something larger, a new picture in which stellar systems are open, dynamic, interconnected, and partially shared with the galaxy as a whole. The Oort Cloud is the structure that makes this new picture necessary. Without it, the old closed system view might have remained tenable. With it, the new view has become unavoidable. And in the next section, we will turn to what this all means for us, why it matters, why anyone should care about a distant region of space we cannot even see directly. The Oort Cloud is so far away, so abstract, so seemingly removed from daily human experience that it is reasonable to ask whether any of this matters. Why should anyone care about a region of space we cannot see, populated by objects we will probably never reach, governed by dynamics that play out over millions of years? The answer is that the Oort Cloud, despite its remoteness, touches human existence in ways that are both practical and profound. Understanding it changes how we think about our place in the universe, about the long-term safety of our planet, about the future of human exploration, and about the very nature of what it means to belong somewhere in space. Start with the practical. Comets from the Oort Cloud have struck Earth before. Not often, not in living memory, but across the geological history of our planet, cometary impacts have occurred, and at least some of them have been significant. The Tunguska event in 1908, when something exploded over a remote region of Siberia and flattened roughly 2,000 square kilometers of forest, may have been a comet fragment, though the evidence is debated. The Chicxulub impactor that killed the dinosaurs 66 million years ago may have been a comet, though most evidence currently favors an asteroid origin. Whatever the historical mix, the simple fact is that long-period comets from the Oort Cloud occasionally fall toward the inner solar system, and a few of them, over geological time, find their way to Earth. The new picture of the Oort Cloud, with its dense inner hills cloud capable of producing comet showers under the right gravitational disturbances, has implications for how we should think about long-term impact risk. The risk is not zero. It is not even constant. It varies over geological time, with periods of relative quiet punctuated by epochs of higher cometary activity. We do not know with certainty when the next such epoch will arrive or how intense it might be, but we know it is possible, perhaps even likely on long enough timescales. Understanding the Oort Cloud is therefore part of understanding our planet's long-term safety, and the kind of monitoring and modeling that astronomers do today contributes to a kind of cosmic situational awareness that humanity is only beginning to develop. This connects to a broader practical implication. As humanity considers becoming a multi-planet species, as we discuss colonizing Mars or building habitats elsewhere in the solar system, the question of how to protect our settlements from cometary and asteroidal impacts becomes increasingly important. A Mars colony, just like Earth, will be vulnerable to impacts. The thin Martian atmosphere offers even less protection than Earth's atmosphere. Building infrastructure on another world means accepting the same kinds of long-term risks that have shaped Earth's biological history and planning for them as best we can. The Oort Cloud is part of that planning. Knowing what is out there, how it behaves, what could fall inward and when, is part of the foundation for any serious long-term human presence beyond Earth. But the deeper meaning of the Oort Cloud goes beyond impact risk. It touches on a question that humans have been asking for as long as we have looked up at the stars. Are we alone? Not in the sense of intelligent life, though that question remains open. In the more fundamental sense of whether our solar system is connected to the wider universe in any meaningful way. For most of human history, the answer felt like no. The stars seemed unreachably far. The space between them seemed empty and meaningless. Our solar system seemed like an isolated bubble in a cosmic void. The Oort Cloud changes that intuition. It tells us that our solar system reaches out across light years, that its outermost members drift in territory shared with the galaxy at large, that material flows between stars on timescales we are only beginning to appreciate. We are not isolated. We are part of a network. The galaxy is not a sparse collection of separate worlds. It is a single interconnected system, with stellar systems serving as nodes in a larger structure, exchanging material across vast distances through the slow currents of gravitational interaction. When you look up at the night sky and see other stars, you are not looking at isolated points of light unrelated to your own existence. You are looking at members of the same cosmic community, each surrounded by its own Oort cloud, each leaking and receiving objects across the gulfs that seem to separate them. The bonds are weak. The exchanges are slow, but they are real and they mean something. This realization carries an emotional weight that is difficult to articulate, but worth attempting. There is something quietly humbling about understanding that your solar system is not a self-contained unit. That the comet you might see streaking across the sky on some clear night decades from now could be a refugee from a star you have never heard of, captured by our sun billions of years ago, finally falling inward to put on a brief show before disappearing again. There is something beautiful about understanding that the icy bodies we have launched probes toward, the ones we have studied with telescopes and learned to characterize chemically, may be partially of foreign origin, telling us about distant stellar systems whose existence we would otherwise know nothing about. The Oort Cloud is a window onto the galaxy in a way that nothing closer to home can be. There is also a more sobering meaning. The Oort Cloud teaches us about the limits of return. It tells us that some journeys, once begun, cannot be undone, that certain regions of space, once entered, change the fate of whatever enters them in ways that cannot be predicted or reversed. This is a lesson with applications far beyond cometary science. It is a lesson about cosmic geography, about the kinds of places that exist in our universe and the kinds of decisions that those places impose on whatever ventures into them. When humanity eventually sends probes or even crewed missions into the Oort Cloud, those missions will not be ordinary journeys with a planned departure and return. They will be one-way excursions into territory governed by different rules. For now, this is hypothetical. No human probe has reached anywhere near the Oort Cloud, and no crewed mission to that region is being seriously planned. The distances are too great, the travel times too long, the engineering challenges too severe. But the future is long, and humans have a way of eventually attempting things that seem impossible from the perspective of any given century. If our species survives the next several hundred years, if we develop the technology and the will to send missions deeper into the outer solar system, the Oort Cloud will eventually become a destination. And when it does, the lessons that astronomers have learned over the past few decades will become directly relevant to mission planning. Anything we send into the cloud will be sent on a journey from which it cannot meaningfully return. We will have to plan accordingly. This is one of the more striking aspects of the Oort Cloud's significance to humanity. It is a region that, by its very nature, demands a different kind of thinking about exploration. The model of the explorer who ventures forth and returns home to report does not apply. The model of the colonist who travels to a new world and stays there is closer, but even that does not quite capture it. The Oort Cloud is not a place to colonize. It is too sparse, too far, too cold. It is a place to study from a distance, to send probes through, to learn from its scales of time that exceed any individual human lifespan. It teaches us patience. It teaches us humility. It teaches us that the universe operates on rhythms that dwarf our own, and that some questions must be approached with a willingness to receive answers across generations, not within them. And these lessons, in the next section, lead us to the questions that remain unanswered, the mysteries that still surround the Oort Cloud, and the work that will fall to future astronomers, future probes, future generations of human civilization, if any of those generations exist to take up the task. For all that astronomers have learned about the Oort Cloud over the past few decades, the deepest questions about it remain stubbornly unanswered. We have made enormous progress in understanding the cloud's general structure, its dynamics, its relationship to the wider galaxy. But the specifics, the details, the precise inventory of what is out there and where it came from remain obscured by the simple fact that the cloud is too far away to observe directly. Most of what we believe about it is inferred, not measured, and inferences, however carefully constructed, carry uncertainties that only direct observation can resolve. The Oort Cloud is, in many ways, still a frontier of ignorance, and the work of pushing back that ignorance is one of the great long-term projects in astronomy. The first major unanswered question concerns the total number of objects in the cloud. Current estimates suggest that there are trillions of icy bodies out there, perhaps as many as 100 billion comets larger than a kilometer or so across. But the uncertainty in this number is enormous. Some estimates run as low as a few hundred billion total objects. Some run as high as several trillion. The variation reflects different assumptions about the mass of the original protoplanetary disk, the efficiency of the gas giants in scattering material outward, the rate of loss to interstellar space over geological time, and the fraction of objects captured from other stars. Without direct observations, these assumptions cannot be tested against reality, and the uncertainty persists. We do not know, within an order of magnitude, how much stuff is in our own outer solar system. The gap in knowledge is striking and humbling. The second unanswered question concerns the boundary between the inner Hills cloud and the outer classical cloud. We have theoretical reasons to believe that the inner cloud has different properties from the outer cloud, but the exact transition is not well understood. Where does the inner cloud end and the outer cloud begin? Is the transition sharp or gradual? Are there subpopulations within each region with their own distinct characteristics? These are questions that current data cannot answer with confidence. They require either more detailed statistical analysis of long-period comets or eventually direct observations of objects in the inner cloud that might become possible with future telescopes. The third unanswered question is the composition profile of the cloud. We know from spectroscopic analysis of long-period comets that Oort Cloud objects contain a mix of ices, organic compounds, and silicate dust. But we do not know how this composition varies with distance from the Sun. Are the innermost objects systematically different from the outermost? Are there compositional clues that could distinguish native bodies from captured ones? Are there signs of unusual chemistry that might point to specific origin processes or unusual environments during formation? Each long-period comet provides a small data point, but the sample is too small and too biased toward objects that have made it into the inner solar system. Direct observation of Oort Cloud bodies at their rest positions, especially with infrared instruments capable of detecting subtle thermal signatures, would transform this aspect of our understanding. The fourth unanswered question concerns the fraction of interstellar origin. We strongly suspect that some fraction of Oort Cloud objects came from other stars, captured during the Sun's early days in a stellar cluster or during subsequent stellar encounters. But what fraction? Estimates range from less than 1% to as much as 50%, depending on assumptions about the density of the Sun's birth cluster and the rate of capture from passing interstellar objects. The truth probably lies somewhere in this range, but pinning it down precisely requires either better data on the chemistry of Oort Cloud comets or better models of stellar cluster dynamics. Both are active areas of research, and progress is being made, but a definitive answer remains years or decades away. The fifth unanswered question is the cloud's response to specific past events. We know that the Sun has experienced many close stellar encounters over its history, and we know that some of these encounters must have produced comet showers. But we do not have a clear chronology of these events, and we cannot reliably link specific events in Earth's history, particularly mass extinctions, to specific stellar encounters. The Gaia mission, a European Space Agency observatory that has been mapping the positions and motions of stars in the Milky Way with unprecedented precision, has provided the data needed to begin reconstructing the history of stellar encounters near the Sun. Researchers are now working through this data, identifying stars that have passed close to the Sun in the past and predicting future close passages. This work is ongoing, and over the coming years and decades, it may produce a clearer picture of how the Oort Cloud has been disturbed across geological time and whether those disturbances correlate with events on Earth. The sixth and most ambitious unanswered question concerns direct exploration. Can we, in any practical sense, send probes to the Oort Cloud? With current propulsion technology, the answer is essentially no. Even the fastest spacecraft we have ever launched, like Voyager 1 or New Horizons, would take hundreds of years to reach the inner edge of the Oort Cloud and tens of thousands of years to traverse the entire cloud. No probe launched today could return useful data within the lifetime of anyone alive now. Mission timescales like that are simply incompatible with the way space agencies and scientific projects are currently organized. They require institutional continuity across centuries, technological reliability across timescales we have no experience with, and patience that exceeds anything humanity has yet demonstrated in scientific endeavors. But the question is not entirely closed. Several proposals have been put forward for missions to the inner edge of the Oort Cloud or to interstellar space more generally. Interstellar precursor missions, sometimes called interstellar probes, would aim to reach distances of 1,000 AU or more within a few decades, using advanced propulsion concepts like solar sails, nuclear electric propulsion, or possibly even more exotic methods. These missions, if funded and developed, would not reach the Oort Cloud proper, but they would venture into its outer regions and could begin the work of studying the cloud's environment directly. Some proposals have suggested using close passages of the sun's gravity in maneuvers called solar Oberth maneuvers to give a probe extreme velocity, allowing it to reach the inner Oort Cloud in perhaps 200 to 400 years. These are not missions for our generation, but they may be for some future generation if humanity maintains the technological capability and institutional continuity to attempt them. There is also the possibility that other observations, made closer to home, will yield surprising insights about the Oort Cloud. The Vera Rubin Observatory in Chile, which began full operations in 2025, is conducting an unprecedented survey of the southern sky, detecting faint moving objects at rates far higher than any previous telescope. Over its planned 10 years of operation, it is expected to discover thousands of new long-period comets, transitional objects between the Kuiper Belt and the Oort Cloud, and possibly even objects in the inner Hills Cloud that come close enough to be detected at their rest positions. This rapid expansion of the catalogue will refine our statistical understanding of the cloud and may reveal patterns that current data cannot resolve. The James Webb Space Telescope, with its powerful infrared capabilities, may also contribute. Although it was not designed primarily for Oort Cloud research, its sensitivity to faint thermal emissions makes it potentially useful for detecting large bodies in the inner cloud or for analyzing the chemistry of long-period comets in unprecedented detail. Future infrared telescopes, both ground-based and space-based, will extend these capabilities further. Each of these instruments and proposed missions represents a partial answer to the deepest unanswered questions about the Oort Cloud. None of them will resolve everything. The cloud is too vast, too distant, too varied to be fully understood by any single project. But cumulatively, over decades, the picture will continue to sharpen. Future astronomers will know things about the Oort Cloud that we cannot even guess at now. And in the next section, we will step back from the specifics and consider what all of this means in a broader, more philosophical sense. There is a particular kind of stillness that comes from contemplating the Oort Cloud, a stillness that has nothing to do with comfort and everything to do with scale. When you allow yourself to truly sit with what the cloud is, what it represents, what it tells us about our place in the universe, something quiet happens. The ordinary concerns of daily life do not disappear exactly, but they shift. They take on a different texture, because you are forced to confront, in a way that is hard to articulate, just how small and brief and provisional our existence is set against the vastness of cosmic structures that operate on timescales we can barely comprehend. Consider, for a moment, what the Oort Cloud actually is in temporal terms. The objects out there have been drifting in their slow orbits for 4.5 billion years. They were placed in their current positions during the chaotic early period of the solar system, when the sun was newly formed, when Earth had not yet acquired its oceans, when nothing more complex than single-celled life would exist for another billion years or more. Those icy bodies had been waiting in the dark, undisturbed in any meaningful way, for a span of time that exceeds the entire history of life on Earth. They watched, in their silent and unobserving way, while bacteria emerged in our oceans. They were there when the first eukaryotic cells developed, when multicellular life arose, when the Cambrian explosion produced the first complex animals. They were there when the dinosaurs walked the Earth for 160 million years, rose to dominance, and then vanished in a single catastrophic moment. They were there when mammals took over, when primates evolved, when humans first stood upright on the African savanna, when our ancestors first looked up at the night sky and wondered what those points of light were. Through all of that, the Oort Cloud has been there, drifting, slowly evolving. Occasionally releasing a comet that fell inward and on rare occasions struck a planet and altered its history. The cloud has outlasted every species that has ever existed on Earth. It will outlast us. It will outlast our civilization, our species, possibly even our biosphere. Long after the sun has run out of hydrogen and swollen into a red giant, long after the inner planets have been engulfed and the outer planets have been disrupted, the Oort Cloud will mostly persist, scattered and dispersed by the changes in the sun's gravity. But its constituent objects will continue to exist, drifting now as truly free interstellar wanderers, carrying the chemical record of our solar system's origins into the wider galaxy. This is one way to understand the philosophical weight of the Oort Cloud. It is a structure that operates on timescales that make human history look like a single heartbeat. Every concern we have, every triumph, every catastrophe, every moment of love or grief or wonder occurs within a single thin slice of the cloud's existence. The cloud does not care. The cloud cannot care. It is not the kind of thing that can hold opinions or notice things. But its mere existence, its patient persistence across spans of time we can barely grasp, offers a kind of cosmic perspective that is worth holding on to. We are brief. The cloud is long. And there is something both humbling and oddly comforting about that contrast. There is also something profound about what the Oort Cloud reveals about the nature of belonging in the universe. We have already discussed how the cloud is a boundary zone, a region where membership in our solar system becomes ambiguous, where objects can be both ours and not ours simultaneously. This idea, when extended, applies to us as well. We think of ourselves as residents of Earth, of the solar system, of the Milky Way galaxy. But the Oort Cloud reminds us that all of these memberships are provisional. They are based on gravitational accountings that could change. The Earth is bound to the Sun, yes, but not absolutely. A sufficiently disruptive event, like a close stellar passage, could in principle alter our orbit, even eject us into interstellar space, though the probability is extremely low over any human timescale. The Sun is bound to the galaxy, yes, but it is moving through the galaxy on a trajectory that will eventually take it through different regions, exposed to different gravitational influences, possibly interacting with other stars in ways that will change the Sun's relationship to the wider Milky Way. We are not anchored to anything in any absolute sense. We are passengers on a long, slow journey through a universe whose configurations are always changing. This understanding can be vertiginous. It can also be liberating. The cosmic perspective that the Oort Cloud offers is not a perspective of cold indifference. It is a perspective that places everything we do in proper context, the accomplishments and failures of any individual life, the rise and fall of any civilization, the biological history of any planet. All of these events occur within a universe whose scales of space and time dwarf anything we can directly experience. To recognize this is not to diminish what we do. It is to see it clearly, in proportion, against a backdrop that gives our actions meaning precisely because they are so small and so brief. We do what we can in the time we have, on the planet we inhabit, with the awareness that the universe will continue long after we are gone. That awareness can be a source of both grief and grace. The Oort Cloud also speaks to something deeper about the nature of exploration itself. Throughout this story, we have returned again and again to the idea that anything entering the cloud cannot truly be expected to return. This is a statement about orbital mechanics, but it is also a statement about something more general. Some journeys, once begun, change the traveler in ways that cannot be undone. Some experiences, once entered, do not allow a return to the person you were before. The Oort Cloud is a particularly extreme example of this principle, but the principle itself is one that anyone who has lived long enough has encountered in some form. Birth is a one-way journey, falling in love, losing someone you love, discovering a truth that cannot be unknown. The shape of human life is full of these crossings, these thresholds, these boundaries beyond which return is impossible. The Oort Cloud, in its way, is a cosmic image of this universal pattern. A boundary zone where things go and become something different, irrevocably. There is something almost spiritual about contemplating this, although the spirituality involved is not the kind that requires belief in anything supernatural. It is the spirituality of attention, of noticing what is actually there, of allowing the universe to be larger than our usual frameworks for it. When you sit with the Oort Cloud, when you let yourself feel the scale of it and the strangeness of it and the patient mystery of it, you are practicing a kind of attention that brings you into closer contact with reality as it actually is. Not the reality of headlines or schedules or daily preoccupations, but the reality of cosmic structures that surround us and shape us, even when we are not aware of them. The Oort Cloud is always there, always overhead, always all around us, in every direction. Its outermost members are nearly halfway to the next star. Its objects are sharing the long, slow conversation of the galaxy in ways we are only beginning to perceive. To know this, to hold this knowledge even briefly, is to be enlarged. To become, for a moment, a participant in something far greater than the small concerns that usually fill our minds. And that enlargement, that brief brush with cosmic scale, is one of the gifts that astronomy offers. The gift of perspective, the gift of awe, the gift of standing under a night sky and knowing, truly knowing, that the universe is vaster and stranger and more beautiful than any of us can fully comprehend, and that we, briefly, get to be aware of it. So we come to the end of this journey through one of the strangest and most distant regions of our cosmic neighborhood. The Oort Cloud, that vast, invisible, almost mythical shell surrounding our solar system, has revealed itself over the course of this exploration as something far more than the simple frozen reservoir of textbooks. It is a boundary zone, a contested region, a place where the rules of our solar system blur into the rules of the wider galaxy. It is the long, gradual doorway through which our sun communicates in the slow language of orbital mechanics with every other star in the Milky Way. And it is the place from which nothing, in any meaningful sense, returns. Think back to where we began. We started with a simple promise. By the end of this video, you would understand why anything entering the Oort Cloud cannot be expected to come back. We have now seen in detail why that is. The cloud's distances are so enormous that the sun's gravity, while still technically present, is so weak that small perturbations dominate the dynamics. The galactic tide reshapes orbits continuously, lifting some objects out and pulling others inward. Passing stars deliver dramatic disturbances that can fling objects in entirely new directions. The chaos of these interactions, accumulated across millions of years, means that no orbit in the Oort Cloud is truly periodic. No object's path is reliably predictable. The very concept of return, of an object completing its orbit and arriving back at its starting position, dissolves at those distances into something closer to a probability distribution, a fog of possible futures, none of which is guaranteed. Add to this the fact that the cloud is leaking objects continuously into interstellar space, that some of its members were never ours to begin with, that the boundaries of our solar system blur into the gravitational territory of the wider galaxy. And the picture becomes clear. The Oort Cloud is not a place from which return is unlikely. It is a place from which return is, in the deepest mathematical and physical sense, almost impossible. The journey out is, for nearly every object, a one-way crossing into a region where the future is governed by forces too numerous and too distant to be predicted. Anything that enters the cloud, whether a comet drifting outward after a close pass with the sun, a probe launched from Earth, or a hypothetical object from a distant star caught by our gravity, joins a population whose collective fate is to drift forever in slow, chaotic motion until something disturbs it again, by which time the disturbing event will be propagating its effects through the cloud in ways no one can fully trace. This is the truth at the heart of the Oort Cloud's strangeness. It is a place that defies the human intuition that exploration involves going somewhere and coming back to report. It demands a different model of engagement, a model in which information flows outward and inward across vast spans of time, in which the things we send out become permanent residents of a region we cannot follow them into, in which we learn about the cloud only through the rare visitors it sends inward to us, the long-period comets that briefly blaze across our skis before being flung back into the dark. But the deeper meaning of the cloud goes beyond this paradox of one-way journeys. The Oort Cloud teaches us, perhaps more vividly than any other feature of our solar system, that we are not alone in the cosmos, not in the sense of intelligent life, though that question remains beautifully open. In the more fundamental sense of being part of a network, the Oort Cloud is our solar system's interface with the rest of the galaxy. Every star, every stellar system has its own equivalent. The galaxy is woven together by these clouds, by these boundary zones where material flows between systems over geological time. We are not isolated points of light separated by empty space. We are nodes in a vast interconnected ecology, exchanging matter and history across distances that seem unimaginable but are, when measured in cosmic time, surprisingly bridgeable. And there is something profound in knowing this. When you look up at the night sky on a clear evening, when you see the points of light that mark the positions of other stars, you are not looking at distant strangers. You are looking at members of the same galactic community to which our sun belongs. Each of those stars has its own Oort cloud. Each is leaking objects into the spaces between, contributing to a slow drift of icy debris that includes pieces of countless stellar systems. Some of those pieces have passed through our solar system already. Some are passing through right now, undetected because they are too small or too dark or too far from any sunlight. Some will arrive in the centuries and millennia to come, visible briefly as interstellar comets that streak across our skis, and then continue onward, never to return. The Oort Cloud is the place where this cosmic exchange happens for us. It is where our solar system touches the rest of the universe. It is where the boundary between us and them, between local and foreign, between native and immigrant, becomes a question of probability rather than fact. And it has been this way for 4.5 billion years, since the day the sun first ignited and gathered around itself the leftover material that would become its planets, its asteroid belts, its Kuiper Belt, and ultimately its enormous outer cloud of frozen pioneers. The first humans to send probes deep into the Oort Cloud, if any future generation manages to do so, will be embarking on a kind of journey unlike anything previously attempted. They will be sending machines, and possibly someday themselves, into the contested zone, into the place where return is impossible. They will be doing so not for any practical reward, not for resources or colonization or territorial claim, but for the most fundamental reason humans do anything in space: to know, to understand, to extend the reach of our awareness into regions previously beyond our perception. And the things they send out will become, in their own way, part of the Oort Cloud, part of the network, permanent residents of the boundary, drifting alongside the icy bodies that have been there since the sun was young. Human contributions to the long, slow conversation that our solar system is having with the rest of the galaxy. That is a beautiful thought, that something we make, something we design and launch and bid farewell to, could become part of the eternal drift, could outlast our species, our civilization, our planet, could carry our presence outward into the cosmic dark long after every other trace of us is gone. The Oort Cloud, in this sense, is not just a region of space. It is a destination for the parts of us we are willing to send and never see again. A place where human creations could persist for billions of years, slowly orbiting in the vast emptiness, occasionally perturbed by passing stars, occasionally drawn closer to other stars, occasionally captured by other systems where, perhaps, someone or something might one day find them. That is why the Oort Cloud matters. Not because it is dangerous, though it occasionally is. Not because it is full of resources to exploit, though it contains vast quantities of water ice and organic compounds, but because it is the place where our solar system reaches out to the rest of the universe. Because it is where the boundary between here and there dissolves into a slow, beautiful gradient. Because it is the place from which nothing returns, but from which everything that is sent becomes part of something larger than itself. The first footprints on the Oort Cloud, if any are ever made, will not be footprints in any literal sense. There is nothing to step on out there. No solid worlds at the cloud's distances, only scattered icy bodies separated by enormous gulfs of nearly empty space. But the metaphorical footprints, the probes, the data streams, the cumulative record of human knowledge about this distant frontier will be lasting in a way that few human creations ever achieve. They will outlast every empire that has ever existed on Earth. They will outlast every language we currently speak. They will be there in the long drift when our descendants, if we have any, look back on the early 21st century as a quaint and distant period in their species' history. Thank you for joining me on this exploration of why nothing that enters the Oort Cloud will ever truly be expected to return. If you found this journey through the most distant region of our solar system as compelling as we did, a like or a subscribe would help this channel continue producing these deep dives into the profound mysteries of our cosmic neighborhood. Share this video with someone who you think might appreciate a long, careful look at the strangest frontier our solar system has to offer. And leave a comment letting us know where in the world you are watching from. We love seeing the global community of curious minds that gathers here to think about the universe together. The Oort Cloud is always there, always overhead, always all around us in every direction. The next time you look up at the night sky, remember that beyond the stars you can see, far beyond, drifts the silent shell of our solar system's outermost frontier. Patient, vast, connected to every other star in the galaxy by the slow currents of gravitational interaction. And waiting, in its own quiet way, for whatever humanity chooses to send into it next.